Okay, I think it's time to start now. Again, hello everyone. My name is Pawan Gupta. I'm a research scientist here at NASA Marshall Space Flight Center, as well as with USRA in Huntsville, Alabama. Uh, Today we are going to talk about actually a new type of observations recently made available from a different platform called Geostationary. Uh, and we will talk about how we can use this geostationary satellite data to monitor air quality. So the today's talk will be more like an introductions to the satellite sensors and some of the fundamental of satellite remote sensing if you have not have any background in the remote sensing. And then this is like a 4 week webinar series. So today's session I already talked about. The session two will talk about the aerosol observations from the two different satellites called GOES-R and GOES-A, which has been launched by NOAA and NASA in the to monitor entire Americas, both North America and South America. And our speakers for that will be Dr. Amy Huff from Pennsylvania State University. She works very closely with NOAA and she works on the application of the satellite data for air quality specifically. In session three, we will try to cover other parts of the world, which is Asia, where we have a number of geostationary satellites in orbits, and there will be few more will be launched in next 4 to 5 years. And for that, we will have Dr. Choi from Yonsei University, South Korea. They are leaders in using geostationary satellite data for air quality monitoring, and Dr. Choi will talk about some of their products and how to access them and where you can use those data. In the session four, we will talk Dr. Prakash Chauhan from Indian Institute of Remote Sensing in India, a part of ISRO, will talk about Indian geostationary satellite called INSET series. It captures data over Asia and Africa, and he will talk about how we can access those data and where those data can be useful for various air quality applications. So before I'll start today's session, I have 2 to 3 questions to ask, and then we will move on. Okay, so let me put the first poll for today, and this is very simple questions. So you have about 30 seconds to respond. Now you should see a question on your screen. How many ARSET training have you taken previously? This is just to get a feeling of what kind of details you need during this trainings and what kind of background you have in satellite remote sensing. So we have about pretty good. So about 34% people are new to our training, and rest of them are actually have taken at least one training, which is pretty good. So some of those who have already taken previous ARSET training, the today's talk may be very introductory for you, and you will see some of the repeat of the information. Maybe it will be a good refreshers. But remember, we have tried to redesign this talk to fit in some of the information specifically relevant to geostationary satellites. So still it will be useful. Okay, so the next question is very relevant to the first ones. Do you have any technical background in satellite remote sensing? If you have taken any courses in your school, college, or guided schools, or if you have done any specific training, including ARSET, it means you have some technical background. If you're completely new, just say no, and please do not worry about that. Like I said, we will do cover some fundamental of satellite remote sensing in today's talk. And I'm just sharing the response with everyone. So 75% people have some background, which is very good, and then 25% people have no background. But please do not worry about that. Those 25% people, we will try to bring everyone on the same page before so that you can start using some of the satellite data. Okay, the last question before we start this talk. And this is, do you use any kind of satellite data for your work? Either it's for research, for your classwork, for your day-to-day quality monitoring, or any other kind of application, water, disasters, land use, climate, anything where you are using satellite data. Um, just select yes if you are not using it current, say no. Okay, great. So this is good news. 80% people are using the data or have used some kind of satellite data in one form or another. And our goal is to bring those 20% people um, so that they can start using some of the satellite data for their work. Okay, thank you everyone for responding to this poll. Now we will get back to the presentation. Let's go fundamental of satellite remote sensing. The first thing is we have to understand what is remote sensing. So those who have already done some training in satellite remote sensing, they know that collecting information about an object without being in direct physical contact with it is basically the technical definition of remote sensing. So you can obtain information about an object without directly physical making direct physical contact. The examples in our day-to-day life of a remote sensing sensors or remote sensing method is very obvious. Our eyes, they do see through things without and get information about certain objects. And then of course the cameras, either it's phone or any kind of camera, they also take pictures and obtain information about certain objects. So these are the fundamental examples which we often or we use in our day-to-day life, which are basically works on the principle of remote sensing. Uh, and we will use this fundamental physics law of getting information about the object from a distance without using something called electromagnetic radiation to learn about air pollution in this talk. Okay, so remote sensing platforms. Once you have this remote sensing sensors or any device which can obtain information without being in physical contact, like a camera, you can put those sensors or device in number of platforms. It really depends on your application and question what you're trying to get information, how much information you want, what kind of information you want. Uh, and how frequently you want that information. So you can put them on a vehicles, on a crane, you can put on the ground, you can put them on aircraft or the drones, UAVs. People also put these sensors on balloons to get a sense of how things are changing in vertical column of the atmosphere. And then of course satellites. So the one within the last, we will talk more about that. So we'll put our remote sensing sensors on satellite and see what kind of information we can get about our Earth atmosphere ocean system from above, from the orbit. Okay, so here are different examples of how we do remote sensing of our planet Earth. And on the y-axis, what you see is the height at which these specific platforms or instruments operates. There are a number of remote sensing sensors which usually we operates from the grounds, which includes the radars to get the weather information. We all use cell phones, so all the cell phone towers are located mostly on the grounds. We have a number of sensors operated nowadays, actually uh, part of your vehicles which get information about the speed limit or the cars in behind you and things like that. And then if you're trying to see more information for to study the Earth atmosphere system, then we start putting this instruments or sensors up in the atmospheres. And like I said earlier, we can put them on a balloon. Aircrafts usually operates around in varying height. They can be from anywhere from 1 kilometer to 10 30 kilometers. And then we have all these small satellites which operates around 2 to 300 kilometer up in the atmosphere, up in the space, and rotates around the Earth to get different pieces of information. And then we have a lot of these polar orbiting satellites, which operates anywhere from 400 kilometers to 1,100 kilometers, and they provides a global view of Earth atmosphere system. And we have been talking about that for a long time, and I'll show you some more examples. And then as you move up in the space, there is something called a geosynchronous or geostationary orbits, which is located about 36,000 kilometers, and that's what we are going to focus in today's in this webinar series. So, what make remote sensing possible? Okay, so you need a energy source. So we utilize something called electromagnetic radiations, and sun is the sole source of energy for that. And once this energy travels through the space, emitting from the sun's, traveling through the space in the form of waves, and each different part of electromagnetic spectrums have a different length of waves, and those are shown actually on the right side. So if you see that spectrum, electromagnetic spectrum, then you will see on the right side is the very short wavelengths or shorter waves, which include X-ray, gamma ray, ultraviolet. And then on the left side, you will see longer wavelength radiations like radio wave, microwave, infrared radiation rates. So most of this energy comes from the sun, but Earth also emits some of this radiation, mostly in in microwave and infrared part of the electromagnetic spectrum. And it is very interesting that our human eyes only sees the visible part of the solar spectrum, which is highlighted on the right side, which is extend from around zero point 0.4 micron to 0.7 micrometer, and that's what we can see and obtain information through. But we can design sensors and instrument which can actually look through other part of electromagnetic radiation spectrum, and we can actually use that in our favor to obtain more information about certain objects in our Earth atmosphere system. So how does the remote sensing process works? So you have sun as a source of energy, which emits lights or electromagnetic radiation in different wavelengths, traveling with different speed, traveling through the space, and in traveling through Earth atmospheres, they interact with components in the atmospheres, which includes clouds, particles, which are often called pollutants or particulate matters, gases, nitrogen, oxygens, and then there are trace gases like NO2, SO2. All those components in the atmospheres interact with the incoming solar radiation. And then once they pass through the atmospheres, they interact with the objects on the surface. So you have trees, water, grass, soils, and built-up areas, which actually get interacted with the solar radiation. And then it either absorbed by these objects, either in atmospheres or at the surface, or it reflects back to the space. So the radiation which reflects back to the space is measured by these satellite or sensors, remote sensing sensors. Now these sensors are very advanced in technology, so they can actually measure radiation in a specific wavelengths only. So they make measurement of a specific part of that electromagnetic spectrum which we have talked earlier. So the intensity of this reflected and emitted radiation to the space is influenced or modified by the surface and the atmospheric conditions. So if you have clouds and if certain wavelengths of radiation is coming from the sun, if it interacts. So depending on the properties of the clouds, it will reflect back to the space or it will absorb by that clouds. So it depends on at which wavelength the radiation is coming and what are the properties of those clouds or particles. Similarly, it interacts with the objects on the surface. So satellite measurements, when satellite make measurements in a specific wavelength, it contain the information about the surface or atmospheric conditions. So you can think about it's like once the radiation is come in contact with one of these object, it actually have a signature of that particular object on that particular radiation band, and which is measured by the satellite. So what satellite measure is just the radiation which is reflected back to the atmospheres or to the space. So how do we use that information to obtain certain to get a physical quantity which we can be used, for example temperature. So for that we use something called retrieval algorithms. So on this slide, what you see on the left side, you have satellite measured spectral radiance. So this is the quantity which satellite is making measure. Satellite is measuring. The spectral radiance means radiance in a specific band of electromagnetic radiation, electromagnetic spectrum. Now, we also use a priori information about atmosphere, surface, vertical distribution, and then we combine that a priori information and satellite measured spectral radiance with radiative transfer theory or the calculations. What radiative transfer calculation does is it simulates the satellite, what satellite will measure under different a priori conditions. So radio transfer calculations are performed, and once you have those radio transfer calculations, then you compare the simulated radiation which is calculated and what is measured by the satellite at that particular wavelength or in particular wavelength band, and when you compare them together, then you can actually obtain information about certain conditions of the atmospheres, and that process is called retrieval algorithm. So the retrieval algorithm is in other ways a inversion problem. Inversion problem means you are trying to simulate what satellite will measure and then what let satellite make measurement, then you compare the two, and then you minimize the error between the two measurements and then obtain information about certain conditions of the atmospheres. And that's how we retrieve geophysical parameters. So the geophysical parameter means which makes sense to us, right? So if you say temperature 30 degrees centigrade or 40 degrees centigrade, you will suddenly realize what it means. Means you will get a feeling about whether it's hot or cold. So something, there are many geophysical parameters which we retrieve from the satellites. One of them is called aerosol optical depth, which we will talk a little bit more, and that specific parameter is used to define how many particles or how much particles are there in the atmospheres. So that we specifically use for air quality applications. So once we have this geophysical parameter, we use them for specific applications such as air quality monitoring or climate monitoring or weather monitoring or any kind of land use, land change or anything. So it's a complex process. We will learn a little bit more about the retrieval algorithm in week 2 and week 3 as well, when the specific speakers talk about the specific sensors and their product. We will go into a little bit more detail about this retrieval algorithm, but it's a very simplistic way of representing the entire remote sensing process. Okay, so I'm going to talk about a little bit more on the satellite sensors and orbits. So let's see. So Earth orbiting satellite remote sensing instruments are named according to their platforms or sensors. So sometime we call them based on depending on their sensors which are on board a specific platforms, sometimes we just call them based on their platform itself. So each platform can have multiple instruments or center. Sometimes a specific platform has only one sensor on board, but often nowadays each platform has multiple sensors or instruments on board. So this is a picture on the right is of the GOES-R spacecraft, which was launched by NOAA and NASA, and recently, and this has a multiple instrument on board it, and you can see those names here: ABI, GLM, which is a lightning mapper. ABI is the sensor which we'll use for air quality monitoring, and we'll talk more about that in a little bit. And then there are other kinds of instruments which are used for different parts, different applications. One is for space weather monitoring. Some of them are for other applications. So this is basic difference between satellite and sensors. So satellite is a platform on which sensors are mounted. Each satellite can have one or more than one sensor. So just remember that. Now, when we talk about the geostationary satellite, and this is specifically applicable one which is launched by US US agency called NOAA, and NOAA actually named them very different. So before the launch of the satellite, they call them GOES-R or GOES-A. So the series start with alphabetic letters. They have before GOES-R, they have GOES-I, O, and all those sensors, spacecraft in the space. And after the satellite is launched, their name changed. The letter is replaced by the numbers. So now GOES-R becomes GOES-16, GOES-S, which is more recently launched, became GOES-17. And once they are operational and in their final orbits and position, they are named as either GOES-East. So the GOES-16 will become, already has become GOES-East, and the GOES-17, right now the GOES-17 is in pilot. Once it is moved to its final destination or final orbit, it will be called GOES-West. So that's how NOAA names these geostationary satellites. So there are many different characteristics of satellites and sensors, and we can actually classify them based on multiple characteristics. So you can classify based on the orbits. So far we have been looking polar orbiting, and then today mostly we'll talk about geostationary. So based on where they are located in the space, that defines their orbits. Energy source, we'll talk about a little bit about that. There are passive and active, solar and terrestrial spectra. Which part of the solar spectrum they are making measurement techniques, resolutions, and finally applications. So come on different characteristics of the satellites. They can be, these are just few, there can be more characteristics of satellite which can be, which can help in identifying different satellite sensors. Here are two common types of orbits, geostationary on the left and polar orbiting on the right. So geostationary satellite has the same rotational period as Earth. So what you see on the left animation, that your Earth is rotating from west east, and you can see the geostationary satellite is in fixed orbit around the equator, and it is always looking the same place on the Earth. So that spot on the Earth over America that's where the measurements are making measurement. This orbit is typically located in about 36,000 kilometers above the equator, and it will look always same spot on the Earth. And the image shown is one typical measurement or the full disk image from the geostationary satellite called GOES-R shown. It's looking both Northern America and South America at the same time. The image on the right side is for polar orbiting. The polar orbiting satellites rotates around the pole to pole. this specific satellite is rotating from north to south pole, and the Earth underneath it rotates. So whatever part of the Earth comes across the path of satellite, the measurements are taken at that particular location. So you can see that the spot on the Earth's surface is changing in polar orbiting, whereas it is fixed in geostationary. So the advantage of polar orbiting satellite is that it provides you global pictures, measurement across the globe. So you can see on the right side image. And that this is one fundamental difference between these two satellites orbiting in these two orbits. The geostationary orbit, often called GEO, or polar orbiting, often called LEO, low Earth observing satellites. So polar orbiting provides global picture, geostationary satellite provide regional pictures. Polar orbiting only can give you observations once in a day or twice a day, depending on where you are located in terms of the latitude, whereas geostationary satellite can provide you very frequent measurement uh, in terms of resolution. It can vary from seconds to minutes to hour. Okay, a little bit more about the geostationary satellites. Like I said, they are about 36,000 kilometers above the Earth. Exactly, it's about 35,786 kilometers, which is about 22,236 miles. The orbital velocity to maintain the uh, fixed rotation as Earth rotation, it's about 3.07 kilometer per second. That's the orbital velocity of the satellite which rotates in geostationary orbit. Their circular orbit at 0-degree inclination with equator. We'll talk that little bit more about this inclination in next slide. And basically, all these parameters are required to match the Earth rotation period. Okay, now talking about there are two terms people often use interchangeably: geostationary and geosynchronous. So geostationary orbit is basically a special type of geosynchronous satellite at the equator. So in this picture, you can see there's Earth. The blue circle is a geostationary satellite which is located at the equator. So when a geosynchronous satellite is is with zero inclination angle with the equator, it is called a geostationary. And then there are other geosynchronous satellite which has some angle of inclination with the equator. So some of the communication satellites are put in geosynchronous satellite and may not, and they may have some kind of inclination angle with the equator plane. So, but both goes all the, I think all of the uh, geosynchronous satellite which we are going to use for air quality application, they are geostationary satellites, so they actually are located at the equator with the zero angle inclination angle with the equator. So this is a big difference between these two, but probably you won't be you won't need this as often, but just to, if you want to understand the technical term between the two, this slide might help you. Okay, so in terms of coverage, we have already seen that the polar orbiting or the LEO low Earth orbiting satellites provides global coverage. You can see how the satellite is making measurement. This is measurements taken from the aqua satellite on the left, and on the right is a geostationary orbit, geostationary satellite, which is in this case goes east satellite or goes R. This is just a loop. So you can see that the measurements are taking up the same place of the Earth, covering both Americas, and they are very frequent measurement. This is every 15 minutes on the right side from geostationary. From polar orbiting, as satellite is moving different places of Earth, it is making measurement, and then it takes almost 1 day to cover the entire globe. Whereas the geostation does not provide you global picture. It looks at one place of the Earth all the time. Temporal resolution or observation frequency. This is a chart showing a typical variability of surface PM 2.5 or particulate matter less than 2.5 micron meter in aerodynamic diameter, mass concentration. So you can see their mass concentration can vary as a function of time. So there can be high values during the morning hours or traffic hours in typical cities, and then depending on how the boundary layer metrology is, uh, their concentration can go up and down, and there can be different concentration during the night time. So the bottom line is the concentration, mass concentration of pollutant near the surface does vary as a function of time. So in order to monitor these changes, you need frequency observations. So if you have a polar orbiting satellite, which we have been using for a long time, like Terra Aqua or the MODIS sensor, they provide only one or two observation. If you are using both satellite, then you will get one observation in data in the morning, one in the afternoon, but that may not be sufficient to provide to see a diurnal cycle of air quality, how things are changing. So that's why the satellite geostationary satellite can actually change that. They can provide every 30 seconds to 15 minutes, depending on which sensor we are using and which place of the earth we are using. And that's the biggest advantage of using the geostationary satellite, that they provide very frequent measurements. There will be some future geostationary satellite specifically designed to monitor air quality, such as Tempo, GEM, Sentinel-4, that will form a constellation of satellite. They will be almost similar type of sensors launched by different countries, and they will form a constellation and will provide, if we combine the data from all of these sensors, then we will be able to make a global picture at very high temporal resolution. And we will see some of those examples in upcoming talks during this webinar series. Okay, so let me introduce to two different satellite sensor. One is called Advanced Himawari Imagers, or AHI. This is on board on a Japanese satellite called Himawari 8 and Himawari 9. And it sees the entire Asia and Pacific. You can see from pole to pole almost. On the left side, the temporal frequency of these observations varies from 30 seconds to 10 minutes. It provides full disk image every 10 minutes, whereas it provides 2.5 minute snapshots of specific areas monitored by Japanese space agency. And then you can also have a mesoscale features, which where you can select a specific area in this disk, and you can actually frequently scan that area every 30 seconds to monitor a specific event. So if you have a fire going on, or you have some kind of a weather system like a typhoon or cyclone, you can monitor them very frequently using these observations. And once you put that information into model, it will help in forecasting that particular event. Similarly, we have over the Western Hemisphere, we have Advanced Baseline Imager, which is on board on the two US satellites called GOES 16, and there will be a GOES 17, which has already launched, which is not yet in the position, but which will capture the western part of the US, including the Pacific. And the GOES East is operational. It does cover up to some part of northern Africa, so you can actually monitor some of the dust storms coming out of the Africa, reaching to the different parts of the America. And this sensor also has a similar temporal frequency of observation from 30 seconds to 15 minutes. So instead of full disk 10 minutes in Himawari, GOES provides 15 minutes. But I think NOAA is thinking in a direction where both GOES can also provide in 10 minutes, so that they can be comparable to Himawari temporal resolution. Once that will happen, we will have a good coverage of entire almost two parts of the globe every 10 minutes. Okay, so the coverage we already talked about, like we have the MODIS and VIIRS in a polar orbiting satellite, which does provides global pictures. In geostationary, we have these three different sensors. GOES 16, which provides America. We have Meteosat 8, which is from launched by ESA. It does cover Africa, Europe, and part of India. The problem with this sensor is this is an older generation of sensors, so it is not as high quality, or it does not have those many number of bands as GOES 16 or Himawari 9. And this is Himawari 9 covering the entire Asia and Pacific region. So in 2020-21, ESA is going to launch a next generation of their Meteosats, third generation, I think third or fourth generation of Meteosat satellite, which will have a very similar to GOES AVI and AHI sensor. So that will be actually complete the global pictures. So once we combine these three sensors, we will be able to capture global picture every 10 minutes. Okay, we already talked about a little bit about this, but there are two types of sensors, passive sensors and active sensors. So the passive sensors rely on the source of energy from the sun or emitted from the earth itself. So they don't have any source of energy. So sun is sole source of energy. It emits radiation. It travels to the atmosphere, reflected back from the earth's surface or atmosphere, and goes back to the space, which is measured by the satellites. These are all ABI, AHI, VIIRS, MODIS, all the geostationary satellite which we often use for air quality application, they are mostly passive sensors. Active sensors have their own source of energy, so they are more like a radar and lidar. They are example of active sensors. So for air quality application, Calypso is an example which is an active sensors. So it does have its source of energy, means it emits radiation, it goes through the atmosphere to the surface. It reflects back from different height, and then there is a big telescope on the satellite which captures that light, and then measurements made. So the active sensors have much more control on what is we are making measurements. So they provide different piece of information. They can provide vertical information, whereas the passive sensors provides more images. Then there are ways in passive sensors which can be used to get the vertical information as well. This is just an animation demonstrating how the active and passive sensor works. On the left, you have passive sensors, which is just making measurements of radiation emitted from the Earth's surface. On the right, you have an active sensor which is transmitting a radar signal. It is reflecting back from the surface, and then it is making measurements. So this is just a demonstration of the two. Now, the next important concept in satellite remote sensing is resolution. But before we move here, I'll take a quick break and then put out a couple of poll question, and then we will move back to our presentation. So you should be able to see question on your screen, and you have 30 seconds to respond. Okay, great. So the question was, geostationary satellite provides global coverage, true or false? So we have seen in many examples earlier that it's a false statement, but it's a tricky question. So if you combine multiple geostationary satellites, then you can get a global coverage. But if you're using only one geostationary satellite, then you will only get a regional coverage. Okay, so just look through some of the slides which we have gone in previously. So this is a big difference between geostationary satellite and polar orbiting satellite. That polar orbiting satellite provides global pictures, whereas geostationary satellite only provide regional pictures. Now, let me. We just talked about a. We just talked about temporal resolution of geostationary satellite, and we talked about how the ABI and Himawari 8, how frequently they are making measurements. So this is a little bit a math question, And how many full disk image are taken by ABI, which is onboard on GOES-R, or also called GOES-16, or currently it's called GOES-East, in 24-hour time period. So just look through the slide. Just we talked few minutes back, and I will give at least 1 minute to respond to this question, because this involves a little bit maths, not too much, but little bit. Okay, so the right answer is 96, and 63% people have responded that. So remember, GOES-R or ABI makes every 15-minute measurements. So if you multiply in 1 hour, there will be 4. In 24 hours, 4 times 24, that will be 96. So there will be 96 full disk image taken by ABI in 24 hours. Okay, great. Let's move on to the resolution, and then the few other things I want to get before we finish. So there are different types of resolution. People have taken already some of the ARSET training. They might be familiar with these slides, but there are spatial resolution, temporal resolution, spectral resolution, and radiometric resolution. And each resolution depends on the satellite orbit configuration, sensor design. Resolutions are different for different sensors. So first, spatial resolution. So the one of the terminology which we often use in satellite remote sensing is called pixels, the smallest unit of an image. When you see any satellite image, the smallest unit in that image is basically a pixel. And this concept of pixel is taken from actually image processing, or from digital computer science. So the digital image is composed of two-dimensional array of pictures element called pixels. This is more a technical definition from digital electronics, and these are arranged in column and rows. So this is shown as on the right side. In terms of satellite remote sensing, pixels, each pixels represent an area or pixel. So it means each pixel represent quantity, a quantitative measurement of and longitude on Earth. That mission one is intensity for the measurement value of that measurement. So and the spatial resolution is basically defined by the size of this pixel, and this pixel size can vary. It can be few meters, centimeters, kilometers, hundreds of kilometers. Here is an example of how spatial resolution can be useful. So you have on right side pictures taken in different spatial resolution, all the way to half meter at the top to 80 meter on the bottom, in the middle of the bottom. Okay, so as you can see, as you start reducing the spatial resolution or increasing the size of the pixel, you will see that the information content started reducing. Means in the half meter you can see things very clearly. You can identify different object in the image. How well you can actually especially separate things. That's what the spatial resolution means here. And as you can see at 5-meter resolution, things become more hazy. You can only see colors varying in different shades, but it will be very hard to differentiate between different objects, between tree and roads and bus and goods or bodies. So the spatial resolution helps us to distinguish different objects or different features in a specific image. The two sensors which we have been talking from, the GST sensor, ABI and HI, they have a 500-meter resolution in certain channels, and that spatial resolution can also be up to 2 kilometers depending on which channel you're using, and I'll show you some more those resolution in a minute. The LEO, or the low Earth orbiting or polar orbiting satellite sensors like MODIS, has about the same spatial resolution. So you can see that the geostation satellites, in terms of the spatial resolution, are competing with the polar orbiting satellites. And they have about the same order of spatial resolution, which was not used to be the case a few years back until we launched Himawari and GOES-R satellite. The spectral resolution. Spectral resolution is basically describes a sensor's ability to define the fine wave interval. Remember the first thing which we talked about, this process of satellite remote sensing. So satellite makes measurement in different parts of solar spectrum. So how fine a satellite can make measurement in certain wavelength band is that's what the spectral resolution is. The finer the spectral resolution, narrower the wavelength range for a particular channel or band. So on the right side, if you have a low spectral resolution channel which varies from zero point 0.4 micron to zero point 0.7 micron, means covering the entire visible channel. So you will have all those colors, rainbow colors, blue, green, red, everything will be have just one value. So satellite will make measurements of all the radiation which falls within this wavelength interval, zero point 0.4 to zero point 0.7 micron or 400 nanometer to 700 nanometer. So you will get only one value for the entire black and white film type things. Now, if I have a higher spectral resolution, if I divide that into 3 different channels, then I can get actually 3 different values: blue, green, and red. And then this will help me in identifying more features. Like I said, each object interact with specific wavelength differently. So depending on which wavelength you're interacting, different object will respond to it differently. So there are multi-spectral sensors like MODIS, ABI, and AHI, and then there are moderate resolution. These are specifically we use for particular to monitor the particulate matter pollution in the atmosphere. And there are hyperspectral sensors which have a spectral resolution of 1 nanometer to half nanometer. And these are basically example of these are like in called OMI and AIRS. And then the futures geostationary satellite like GEMS and TEMPO, they will be also hyperspectral resolution, and they are specifically useful to monitor the gases pollution. And we will learn about that in week 3, when we talk about the GEMS and some of the Korean satellites where they are using this technique to make measurement of gases polluted. These are the number of bands in both ABI and AHI. On the left is AHI, right is ABI. You can see that both ABI and AHI are almost identical, except there are few differences between these two sensors. Both have 16 number of channels in each sensors. There is a green channel at 0.51 in AHI, which is not there in ABI, and there is 1.8 channel in ABI, which is used to monitor the cirrus cloud in the atmosphere, which is not present in AHI. So there are some minor differences between ABI and AHI. Otherwise, they are very identical sensors in terms of the technology, in terms of the measurement. Radiometric resolution is basically how you represent the data in your, how well you can actually, how precisely you can store the data on board satellites. So image data represented by this positive digital number, which is also called a binary number system, and this varies from 0 to a selected power of 2 to power 2 minus 1. The maximum number of brightness level available depends on number of bits used in representing the energy recorded. So that is called, the number of bits are basically called radiometric resolutions. So if you have a sensor which can only reports 1 bit, means 2 to the power 1 minus 1, so it will only have a 2 grade level values, 0 and 1. So you can only see through the satellite either black or white. If you have a 4 bit, then you can divide that into 16 different levels, 2 to the power 4 minus 1, which is 16, so 0 to 15 different levels. And this is very important because depending on how many bits you can record on the satellite sensors, how precisely your measurements will represent for certain quantity. So in case of ABI on GOES-R and S, they are about 12 bits measurements, and there is a 3.9 micron channel which is used to monitor the fires, which is a 14 bits because you need more precision there. So they have made it a little bit more high radiometric resolutions. This is an example of how radiometric resolution. I'm going to skip this in interest of time. I just have 5 minutes and I want to go through some of the other things. So this is again showing same kind of concept that as you have more number of levels available to record the energy on the satellite, you get more details about certain objects on the Earth. So in case of GOES-R ABI, you can record the energy in 4096 different levels. Temporal resolution we already talked about. In polar orbiting, the swath width of a particular satellite defines how frequently a satellite will make measurement around the globe. In case of MODIS and VIIRS, they are 1 to 2 days per measurement. The resolution is 1 to 2 days. In case of geostationary, it can vary from 30 seconds to 1 hour, depending on which sensors and satellite and which location you are. So trade-off. It is very difficult to obtain an extremely high spectral, spatial, and temporal and radiometric resolution all at the same time. So there is always trade-off, and this basically boils down to what is your application, what you want to achieve, or what you want to get from certain satellites. And based on that, you compensate one specific type of resolution from another. And but technology is helping us. In recent 5-10 years, the technology has improved a lot, and we were able to actually achieve very high resolution in all kind of resolution. With that, I have a lot of references if you want to get a little bit more on satellite remote sensing and how we are using them for monitoring Earth atmosphere system. You can go through some of this link and you will get a little bit more in-depth information about satellite remote sensing process. Now, briefly, I'm going to talk about few tools. I'm sure you will learn about these tools in coming sessions, week 2, week 3, for a specific satellite. I just want to give very quickly overview of there are global geostationary meteorological satellites operated by individual countries. We already talked a lot about the GOES, which is launched by United States of America, which looks both North and South America. There is also European Space Agency's monitors series of satellites called Meteosats, and those are basically looks over Europe, Africa, part of Indian Ocean and India. Himawari is Japanese, launched by a Japanese space agency and maintained by Japanese Meteorological Association. They are Himawari 8 and 9. They are very similar to GOES satellite. They were launched Norway. There are 2 Himawari in orbit right now. China has their own called Penguin. There's a series of Penguin satellites, and then India has its own called series of satellite. And on the table on the right, you can see actually all the list of different geostationary satellites by various countries, and this is the link for a reference paper which was just published. It reviews geostationary satellites and how they can be used for air quality applications. So this is a nice paper if you want to get a global feeling of how and which countries have what kind of capability in terms of geostationary satellites. For GOES-R, people who are in America or people who wants to use the GOES-R data for any application, this is a nice reference paper for GOES-R or the ABI on the GOES-R series of the satellites. Both actually GOES-R and GOES-S. So this was published in BAMS, Bulletin of American Meteorological Society, and the link, it's an open access article, so you can find this link. Okay, great. So now, since we have learned about satellite remote sensing of geostationary satellite and how they are different than polar orbiting satellite, I'm going to go over some of the tools available online for visualizing some of the images and data products from these geostationary satellite both GOES-R and Himawari. Throughout this webinar series, you will also learn about more tools from other agencies, including NOAA, NASA, and JAXA, and Korean Space Agency, to visualize some of their product in respective webinar series. So first of all, I will go over this NOAA geostationary satellite server. It's a main website operated by NOAA, which hosts a lot of imageries in real time to visualize through various sensors. So in order to provide a demo, I will go to the website and will share you my browser so that you can, if you like, you can browse along with me, or you can take a note of certain features in that website. So let me open this on my browser. So this is the website. Again, it's called NOAA Geostationary Satellite Servers. As you reach on the home page, you will see the imagery at glance. Since it's operated by NOAA, so most of the images shown on the home page are from the US, but I will show you to look things for other parts of the world from different satellite. So you can see West Corners, Alaska, Hawaii, and the tropical Pacific, three different regions which are highlighted here. And there are three different types of imageries shown on the home page. One is infrared, visible, and then water vapor. These are mainly used for weather monitoring. So I will show you other channels how to access. Now, if you look on the left side, there is a vertical bar. And there are many good resources available on this site. So you have a channel overview, site disclaimer, and then if you go to the full disk, you will see GOES, which is this one, Himawari 8, which is a Japanese satellite, Indian Ocean using a Meteosat satellite, and then the Meteosat which is showing the Europe and Africa. And then you can see other things like you can see images for a specific region, Pacific Northwest, Rockies, or any of the regions in the US like Great Lakes or Northeast. You can go to those specific website and look at that. And it also has a lot of other information as well. So let me go to GOES full disk. When I click on the GOES full disk, it takes a little bit, but it will take you to the page where you can see the GOES data for the entire full disk. And when I say full disk, means it covers both Northern America and South America and good part of the Pacific Ocean. Now, depending whether you are looking the GOES west or GOES east, you will see different coverage area. So these images, what you're seeing right now is coming from the GOES west, which is a older version generation of satellite, and this will be replaced by GOES S satellite, which has been recently launched. Then if you scale down, you can see the Meteosats. So Meteosats will show you Africa, Atlantic Oceans, part of South America, and the Europe. Then there is a Himawari, which goes again, it's very similar to GOES-R satellite. This shows part of Asia and Pacific Ocean, including Australia, and it covers all the way half of India. So you can look all these satellite images up here. Now, for specifically for air quality, these images which are shown on the home page may not be relevant. So what we can do is we can look through the GOES full disk, and then it will take you to, let me see, hemispheric, continental focus, regional west, GOES east. And if I click on the source, then you will see a different page where different part of the US are divided into 10 different pieces, and you can actually see each region. So I can click on the southeast, and then I will see enlarged image of the southeast for each band of the GOES. So this is a geocolor image, which is more like a true color image, and then you have individual bands to see specific land, atmosphere, ocean features, those channels. Now, if you go on the top on this page, then you will see many different options. So for example, I click on the Go Full Disk View, and then I say GeoColor. So it will come up with this image, full disk image. This is the latest image GOES-R satellite has acquired on September 10, 11 UTC, which is very close to current time. And then you can change, so you can actually see the previous image by clicking here. Uh, and this, since this has a huge image, very high resolution data, so it take a little bit while to actually load in your browser. So you can see now the animation. You can see some of the cyclone system which are currently active in Atlantic Ocean. There are 3 systems here. You can see the weather patterns over Northern America, and you can also see one of the features specifically relevant to air quality is there's a lot of biomass burning happening in South America. So if you focus in this area, Brazil and this Peru and other parts of the South America, then you will see uh, actually smoke coming out of this fire transporting along with the system over the Pacific Ocean. You can also see a sun glint moving from Atlantic Oceans to the Pacific as the time of the day overpasses. So this is very nice visualization animation for this from the GOES-R satellite. You can look specific band here. So for example, relevant to again air quality, let's see, you can see IR CO2 long wave. This is the band which is used for CO2 monitoring. It's called IR CO long wave band. You can see all the systems actually how they are responding. Then you can see IR band number 12, which is kind of to see how the ozone things are working in the atmospheres. You can see band 3, which is for vegetation, so you will see more things. This is night time and it's taking just time, so you can see how the vegetation things are changing in time. But this is very high frequency, high temporal resolution images, so you won't see much changes over land in this specific channel. You can download the animation here by clicking this button. You can also go to specific regions, Caribbean and Atlantic. This is one of my favorite because I like to see how the dust is transporting from the Northern Africa or Saharan deserts to US and other parts of America. So if I click on the tropical mid-wide view geocolor image from these regions, then I will see part of Africa. This is the same zoomed in version of the image which we saw in the full disk, but you can see Northern Africa, the desert area where a lot of dust storms originate, the transport with the weather system. You can see some dust transporting actually. If you can see around those tropical system or the hurricane system, you will see some brownish color, which is nothing but dust on the top. On the bottom, this is a sun glint, so this looks very similar in color, but on the top, you will see some dust features, which are basically dust originating from the Africa and transporting across. So this is a very nice tool. I would strongly encourage everyone to browse it, spend some time, and you will find a lot of good, interesting imageries here. Okay, let's move on. So the next one, I already talked about this. This is the same thing which we just discussed. Another one is called Slider. This is operated by Colorado State University. Again, this is a CIRA, a center by NOAA, and this allow you to visualize full disk image of GOES-R or the ABI sensor, Advanced Baseline Imagers, or the Himawari sensors together here. And you can select different channels. In the earlier page, you can only visualize image for past 24 hours. This tool allows you to go a little bit beyond that. So let's go over this tool in a browser and then we can look how this works. So I'm going to open my internet browser, and this is the tool which I was talking. So once you open this tool, On the left hand sides are all the controls. You can actually stop the animations and see the full disk image. So this is like current image taken by GOES-R satellite. You can select a speed here. You can zoom specific areas. You can put lat-long boundaries if you want. So if I click lat-long, then it will show lat-long grids on this. And then slider is basically something you want to, if you have a multiple layer, you can slide through those layers. Then you can also draw a mouse. So suppose I'm interested only in this regions, I can make a box, and then if I play, then I actually can focus on that area within that box. So this is very good when you're trying to monitor transport of some of these particulate matters or aerosols which are relevant for air quality, and see where they are moving. So this is nice features. And now if you go down, you can select the satellites. Like I said, it has two: GOES 16, which is GOES East, and it also has GOES 17, which will be eventually GOES West. So if I select GOES 17, then you will see slight shift in the coverage area. Now it does cover entire America, but it covers more western part of America. And then uh, so right now this specific GOES 17 satellite is in parking position, means it's not at its final destinations. Once it is on its final destination, you will see the coverage will further change. It will cover America, but it will not cover entire South America. And then you can also select Himawari 8, which is a Japanese satellite. It shows the view of Asia, including Australia. As you can see in the image, right now it's nighttime in most of the area. So you see a nighttime image here. Now you can select the product, GeoColor. You can again choose a specific wave band. So there are 16 band in both GOES-R and Himawari satellite. You can specifically choose each of these band. And then there are some product which you can choose. So there is RGB air mass, which you can choose. So again, this is a night time, so you will see not much going on there, but you can actually show some of the other, like fire temperature, which is kind of fire detection in that region. You can see from both GOES-R and Himawari. Let me put again the GOES East. So if I choose fire channels here, let's see what it shows. So fire temperature. So you can see some activities happening actually in the southern Africa, southern part of the America, Brazil, and this area. Let's see. There are some other product which may be useful. Ash from ARSET. There is a dust also. So this specific combination of different channels is actually designed to visualize some of the dust. So the dust is looking like this one here. So you can see some coming from the Africa continent. They're not very prominently visible here, but if you zoom in a specific area, you can see them. You can choose to add layers on top of each other. You can also see how many images you want to see in that loop. So 6, 12, 60 number. You can also choose the time step. For GOES-R, the images are available every 15 minutes, but if you decide to choose coarser time resolution, you can say 1 hour or 2 hour images. So depending on your need, you can choose that. You can also, there is called archived imagery. You can also go and choose the dates, beginning dates. So here you can notice actually the images are available all the way from July 28, which is almost 45 days actually from now. So as compared to the earlier tool where we can only see last 24 hours images. Here you can go back in time up to 45 days and look for any of the images. So you can select the beginning date, beginning hours, and then within hours what specific minute, and you can produce those loop here. You can share the URL for a specific, just like we did in other tools like worldview, and that will be so. Again, this is very useful tool for visualizing near real time or real some of the recent past events uh, for both goes R, goes and goes S, which is goes 17, or the Himawari for your future reference. Okay, so let's move on to the next tool, which is called a AHIB viewer. So this is specifically only for advanced Himawari imager on board on Japanese Himawari 8 and 9 satellite, and this tool is called P-Tree. The P-Tree tool is hosted by Japanese Space Agency, JAXA, and let me go to this tool and then we can see how this works. So this is the home page of P-Tree system. It's again JAXA Himawari monitor. You can actually register here. There are user guide to download the actual data. But in order to see the images and some of the product here, you don't need to register. Now, one thing you will notice here is that the tool is displaying the images a little bit differently than what NOAA has been doing. They are trying to display on a more cylindrical map projection rather than more spherical Earth projection. So on the left, you have a time to select. Again, by default, it will show most recent image. I have selected this image for September 10 at 4 GMT at 30 to 39. Remember, Himawari 8 and 9 provides full disk image every 10 minutes as compared to 15 minutes from the GOES-R. You can also go back in time, like latest image, 10 minutes plus 1 hour, 1 day. So you can select how advanced you want to go by minutes, by hours, or by day. On the left, you see different overlays. You can select coastline, latitude, longitude, grids, major rivers. You can click off any of those things and then will start showing on the map. This system, what I found is relatively slow, so you have to be a little bit patient with the system. Eventually, it will work. They are trying to improve it, but it's just the nature of the system, because remember, these data are very high resolution in the space time, so it takes a lot of space and computing processing to manage this kind of tool. Then there are JAXA products. So sea surface temperature is the one. If you click, you can see the temperature laid on top of your RGB image. If you can again zoom in using this plus minus sign here, and then if you go a little bit on the bottom, you will see this color scale. So this is sea surface temperature color scale, which you can see. You can also see aerosol optical depth, which is relevant for air quality application. And let's see if it shows up. Now, this specific product is derived product. Again, you can see the aerosol optical depth has started showing up. The scale is from 0 to 5 in this case. And this product is derived using a Japanese algorithm. You can see some part of China showing values as high as 4 or 5 here. You can see chlorophyll concentration over ocean. This is chlorophyll. Again, you can see along the coast very high values of chlorophyll concentration. Wildfires. So this is a fire detection by Himawari from the geostation satellite. Again, it only shows the locations of the fire. And let me see if I can actually show the blank or GSI map, and then add the fire location, RGB image, and then I'm going to change the, let me try to change the opacity of these RGB image so you can see the fire more prominently on the side. Somehow it's not responding very well for the fire layer, but it is there. And then there is other product like cloud optical thickness and other product are as well available. Again, it's very nice tool. If you want to use the Himawari data, you can register and you can get actual data from any of this product. So this will be very useful. We will learn more about Himawari and their aerosol product by our colleague from Korea on week 3, where he will show some of the results from how the retrievals corresponds with the ground measurements and how people in Southeast Asia and Asia have been using for various air quality application, including forecasting. So this is another very important tool. With that, I think that's all I have. Again, thank you everyone for joining, and we will take question answer now. Thanks. Okay, so I'm going to start the question answer session now. If you have a question, please type into the question sections of the control panel in GoToWebinar. Now, I will start answering some of the questions which you have already typed throughout the presentations. The question 1, from which source we can take AVINH data in to use in research purpose? Okay, so in my PPT, I have a couple of sources where you can get the ABI and AHI images, but these are just images. In week 2 and week 3, we will actually learn more on how actually to get the actual data which are relevant for air quality applications. So please hold on your use of the data specific geophysical parameter until week 2 and week 3. We will learn more about the data sets, and then we'll also learn how to get them. Question number 2, will we get practical training on MODIS data and how to use this data for aerosol monitoring? No, not in this webinar series. This webinar series is only focused on geostationary satellites. If you are interested on MODIS data, we have conducted number of webinar series and in-person trainings, and material of those training levels on our website at arset.gsfc.nasa.gov. You can download and watch recording from the previous webinars. Is there a particular reason to use these specific angles in GOES 15, 16, 17? Okay, if you are asking about their position at the equator, then yes. The specific reason for putting these GOES 16, 17 or any GOES east or west, so that you can get the required geographical coverage for monitoring various weather events. Remember, these GOES satellites are specifically designed for weather monitoring, but in recent time, due to advancement in technology, advancement in number of channels, we have been using them for air quality application as well. What is the spatial resolution of air quality data from the geostationary satellite? It will depend on which algorithm, specific algorithm which we are going to use. The original resolution of the sensors varies from 500 meter resolution to 2 kilometer resolutions. Most of the aerosols data will come most likely into 4 kilometer resolutions to 10 kilometer resolution. Again, we will talk about those things in week 2 and week 3. Is there a method to calculate uncertainty of remote sensing in each application? So there's no one method which can be used. Each uncertainty in each retrieved quantity has to be calculated in certain ways, depending on that quantity, depending on available ground truth data, and depending on the method of remote sensing which we are applying. So there is no one method which can be used across different application or different parameters. Do you know any geostationary satellite providing AOD data for Turkey? So I believe the INSET series from the India, um from India, which is should cover Turkey as well, but I'm not 100% sure. Also, the satellites, Meteosat satellite by European agency should also cover Turkey. Uh, they have some AOD data products, but I'm not very much familiar with those products yet. But please try to tune up in seminar week number 4, where we will talk about the INSET data INSET series of satellite, and there you will be able to see if Turkey is covered by that satellite or not. What is the use of radiometric resolution in remote sensing? It depends on satellite hardware. Yes. Yes, satellite radiometric resolution depends on satellite hardware. It is basically the precision at which you want to record the measured radius. So, for example, you have only two bits and your satellite has measured some number, one, um, 0 and 1. It can only record 0 and 1. But if you have more than two bits, then you can go into decimal places, 1.1. How far in decimal places you can go, that is determined by the radiometric resolution. So you can, it's very simple example, right? How accurately you can represent the value of pi, which is 22 by 7, right? You can use 3 digit after decimal, you can use 6 digit, 9 digit, 12 digit, 100 digit. So that is how many digits you can go after the decimal. That's in simple language, that's what the radiometric resolution actually defines. More radiometric resolution you have, you can distinguish between two close object or two values more accurately in real life. So if you have a higher radiometric resolution, you can distinguish between 2.1 micro 2.1 microgram per cubic meter versus 2.2 microgram per cubic meter. If you have a low radiometric resolution, then that difference will be not be able to resolve. So it has very specific application and it's very important resolutions. Okay, next question. Okay, does pollution level at place affect the radiometric resolution of the image? No, the radiometric resolution is fixed and it's fixed for specific channels and a specific sensor. It does not depend on the level of pollution. How you convert satellite data into microgram per cubic meter concentration? Again, this has to be done using some kind of modeling, either physical modeling or statistical modeling. We have number of webinar series conducted on this specific topic, and you can find all the material on our ARSET website to go over that. What is the accuracy of calculated surface PM 2.5 based on AOD? Again, it depends on what method, which part of the world you are using, which data of AOD you are using. It varies. It varies by many factors. Again, if you're interested about more on AOD PM 2.5, like I said, we have conducted number of webinar series specifically talking those topics. and you can get more information from the ARSET website. Next question, how we can obtain quantitative information on wildfire intensity in burnt area. Again, this is a specific product from different satellites. Uh, we have this product from polar orbiting satellite like MODIS and VIIRS, and we will also have this same product from the geostationary satellite like GOES-R and Himawari. Uh, Irrespective of the satellites, these products will include the locations of the fire where the fire has been detected, means latitude and longitude, confidence level, what is the confidence of satellite at which the fire has been detected, is there high confidence, low confidence, and it will also calculate the area, burnt area into certain pixels. So these are all the products available. If you want to get a little bit more onto that, ARSET's land application training program has conducted several trainings in that specific topics, and those materials are also available on ARSET website. What is the difference between ascending and descending satellites? So the ascending and descending satellites are basically how the satellites are moving, whether it's moving from north to south or south to north. This is mostly applicable to polar orbiting satellites. So ascending means it's going from south to north. So Aqua is an ascending satellite, whereas Terra is a descending satellite. It's going from the north to south. Does the message scale view from GOES-16 record in all 400 pixel intensity levels? Yes, yes. Irrespective of which mode it is, all the channels, all the 16 channels of GOES-16 or GOES East records those values in those different intensity levels. That's basically a radiometric resolution. Aerosol cloud interaction can be studied by Himawari. Yes, short answer is yes, but I will not comment on that further because this is more a climate question and we do not cover here in this specific training. What are the most useful sensors to evaluate the fluctuation of air parameters? I'm not sure if I understand that question properly. So if you want to rephrase it, I will be happy to answer. Next question. Is it fair to say that LEO satellite have more product related to air quality than the geostationary? At present, yes. Uh, because there are satellites already in orbits and they have been operating in operation for a number of years, almost 20 years, some of them like this, and they definitely have more products for air quality monitoring. Geostationary satellites for air quality monitoring are new generation of satellites, so they are developing currently. In next 5 years, they will also have more air quality related products. But in today's condition, yes, LEO has more products. Question number 17. What new campaigns are in work to disentangle data within columns from satellite measurement, particularly air quality measurements? Okay, I'm not sure if you are talking about field campaigns. Then there have been a number of field campaigns in the past, and some of them are ongoing, including Discover AQ and Course AQ from NASA and Korea with Korean partnership, which specifically uh, try to understand this column to surface relationship. Can we use satellite data to study the local air quality like a city or a part of country? Yes. Uh, Currently, satellite data have the highest resolution air quality data from satellite is about 750 meter from viers. So you can definitely use those kind of data to study air quality at city and a specific part of the country. Okay. The next question is what is kappa coefficient and how to calculate it? I'm not sure what is that. We haven't talked about anything about this in this webinar series. What is the difference between geostationary and geosynchronous? Okay, as we talked in our presentation, and let me show it's slide number 17. If you go to the slide number 17 is today's presentation. The a geostation satellite is a special type of geosynchronous satellite which is located at the equator. So that's the main difference. So all geostation satellites are geosynchronous satellite, but geostation satellites are located actually at the equator. Does cloud cover interfere with the satellite data and how it is managed? Yes, cloud cover does interfere. Specifically, the satellites which make measurement in UV and visual part of solar spectrum, cloud is a big problem. If there is a cloud, we cannot essentially make any measurements of air quality. So all the data which are taken during the cloud cover condition are masked for air quality application, and we do not retrieve any information for air quality on those spots where clouds are present. How to get wind speed and direction data? Again, I'm not sure how you get that. There are ways to do that from the geostationary and from polar orbiting, but we are not covering that in this webinar series. Question number 23. Will we get some advice or tools on how to download graded data and how to open it up? In Not in this webinar series. In this webinar series is a introductory webinar series for geostationary satellite and their data product. Currently, we do not have any gridded level 3 data product from the geostationary, but remember the geostationary data are from fixed orbit, so they are actually already gridded in a way. They are fixed in terms of their spatial position on the earth. So in one sense they are already gridded data. We will look through how to get some of those, not going to how to open those data, how to analyze those data here in this series. Maybe in future we will conduct more trainings on doing that. Question 24, which is the best for cloud and PM 2.5, AHI or AVI? Both are, like I said, both are almost identical. Again, it depends on your application. AHI make measurement in Asia, AVI makes measurement in over America. So it depends on where you want to use. Both have similar capabilities. Is it possible to scale down AOT estimates somewhat finer spatial resolution, say 500 meter or lower? In theory, yes, but there is no operational product for such thing. You can do that on a research basis. You can develop some kind of mathematical technique to do that. Some people call it oversampling. So you can oversample data over time period. So you will lose the temporal resolution information while and you can improve the spatial resolution in that process. Okay, question 26. Concentration of gases from emission source don't diffuse through atmosphere according to Brownian movement. So how can I measure more precisely emission points, or we just estimate average concentration of gas on atmosphere? Okay, I don't understand that question fully, but I'll say this, that satellites estimate emissions or concentration of certain quantity for the entire pixel of that measurement. So if pixel size is 500 meter or 1 kilometer or 10 kilometer, you will see one value, average value for that large area. So it's not. Question 27. How active sensors helps in air quality monitoring? Is there any open data? Yes. Again, this has been covered in number of webinars. We have been doing that for a long time. All of the NASA data relevant to air quality or other applications are open data. You can download from the various websites. We talked about these in various webinar series which we have done in past. So please try to look over some of the material which we have on our ARSET website to learn a little bit more on that. Can the satellite data of AOT be used for hyperlocal or micro level community studies? What is the level of view covered by one pixel? So I believe you're asking about the spatial resolution. The spatial resolution from the geostationary satellite varies from 500 meter to 2 kilometer spatial resolution. From polar orbiting satellites, the data which we have for air quality monitoring varies from 750 meter resolution to 10 kilometer resolution. Question 29. How AOD converted into PM2.5 concentration? Again, please go through the website, and we have done webinars in the past which will help you to understand that problem. Okay, question 30. There are other NASA training program that covers taking level C data from other sources and use Python to plot the data and enable exporting for others use scenarios. That is true, but I'm not sure what is the question here, so I will leave it there. Okay, I think we have tried to answer all the questions. If you have more questions, feel free to email me, and I will see you all next week. We will have a guest speaker, Dr. Amy Huff. She will talk about the GOES-R and GOES-S satellites and their data products and some use case applications. Thank you everyone for attending. Have a good day. Bye.